In this video, we discuss applied optimization, so those are just word problems, for functions of several variables. Now we're still using the same second partials test that we used at the beginning of this section on optimization, but we've got a few extra steps, a few extra things to keep in mind when we're solving word problems. So you're going to read a paragraph and they're basically going to ask you to optimize something. They're going to ask you to find a minimum or a maximum of something. After you read that paragraph, your first job is to find the function that you're optimizing. We're going to call that function the objective function. This is standard language in the field of optimization. So we call that the objective function. Now, if our objective function involves more than two variables, if it involves three variables or more, because we're in Calculus 3, we need to write it as a function of two variables. We don't have a three-variable version of the second partials test, not in this class. It doesn't mean it's not out there, it absolutely is out there, but as our first introduction to this, we're only using the second partials test on functions of two variables. So if your objective function has more than two variables, you're going to have some constraint equation or equations that will allow you to write your function entirely in terms of two variables. So if I've got a function of x, y, and z, there's going to be an equation out there that's implied by the word problem that tells me how x, y, and z are related. And with that equation, I'll be able to replace x with a function of y and z, or y with a function of x and z, or z with a function of x and y. So I'll be able to write the objective function entirely in terms of two variables only. That's not always the case, but it will be the case in our class because we only know how to optimize functions of two variables with the second partials test. So you're going to get a function to optimize. You write it in terms of two variables using some constraint. Sometimes, instead of calling this the constraint equation, people will just call it the constraint. And then you'll optimize the function using the second partials test. Now, of course, when you're doing this with the second partials test, you're going to come up with all kinds of answers. Some of them might not make any sense in terms of the application. If you're trying to find a maximum or like dimensions for volume, well, dimensions all have to be positive or possibly zero. You're never going to have a room that's negative 12 feet wide. It's either 12 feet wide or it's some other non-negative number of feet wide. It's never negative 12 feet wide, if that makes sense. So you need to restrict your domain to those answers that are realistic for the function that you're optimizing. So that's just a for instance, lengths and distances, they shouldn't be negative. So we'll optimize the function, we'll keep in mind the real world interpretation of what it is we're doing, and then hopefully we'll have enough information to answer the question. Now the problems that we're about to do today are a little bit contrived. The first one is a problem that just allows us to walk through the method, and then the second application problem is a little bit contrived, but it's a good application of applied optimization. There are some great examples from like physics and like business, economics, biology. There are all of those, but I actually took all of those good examples for the reassessments for our class. So unfortunately, there weren't a lot of examples left over in all the textbooks that I use frequently to give you some new examples for these videos. But I think the examples that we'll do in this video will illustrate the method well enough that you'll be able to solve the more interesting problems on your quizzes and reassessments in our course. So let's look at this first example. It asks us to find three positive integers, x, y, and z, satisfying the following. So x, y, and z are positive and they're integers. And we know that their sum has to be 32, and we want to maximize this function. So this is the objective function. because that's what we're trying to maximize. They ask us to find a maximum. And they also give us a constraint. It's implied in this statement. We know that, let's actually have two constraints, or four constraints, depending on how you look at it. We want the sum of those three positive integers, to be 32. So that's a constraint. I know that x plus y plus z, that's their sum, has to equal 32. And then I also have three other constraints. X, y, and z are all positive and they're integers. I guess I have 6 constraints really, but I'll write that down as well. X, y, and z are positive. X, y, and z are integers. Okay, so we want to keep all of those in mind when we're maximizing this function. Now the problem is right now it's a function of 3 variables and we only want it to be a function of 2. Well, that's easy enough. Because of this constraint, I can write z in terms of x and y pretty simply. So I'll take my constraint equation and solve it for one of the variables in terms of the other 2. Okay, so I'm just walking through this and I'm solving it the way I typically would, but let me write out the steps for you so that you can follow these steps at home. You want to first identify the objective function, and that's the function that you're trying to minimize or maximize. And we just did that. We said the objective function is p equals x times y squared times z. Unfortunately, this is a function of 3 variables, not 2, so we need some constraint. So then from here we want to identify the constraint equation. And next we want to use the constraint to write our objective function in terms of 2 variables only. Because we're in Calculus 3 and we only can optimize functions of 2 variables with the version of the second partials test that we've discussed. So our objective function was this. Our constraint was that the sum of our 3 positive integers has to be 32. So x plus y plus z equals 32. And now we want to use the constraint to write this objective entirely in terms of 2 variables. So more specifically, what is that going to require? We'll have to solve the constraint equation for 1 variable in terms of the other 2. And then you substitute that into the objective function. Okay, I see that this is a little bit blurry. I'm going to use focus on my camera for just a second. I'm sorry, it's going to look a little weird, but I think it might help. Yeah, it is. It's a little bit better. Okay, so that's what we're going to do. I'm taking this equation. I'll solve for z in terms of x and y. So I have x plus y plus z equals 32. So if I subtract x and y from both sides, we have z equals 32 minus x minus y. And then we substitute that into the objective function to write our objective as a function of x and y only. So I've got x times y squared times z, and z happens to be this 32 minus x minus y. Now I've got a function of 2 variables, and I want to find a maximum. So I can use the second partials test to maximize p of xy now. Okay. So we'll distribute. We have 32xy squared minus x squared y squared minus xy cubed. And the first thing we need to do when we are using a second partials test is we need to find the critical points. And the way we find the critical points is we find the gradient of p and we set the gradient of p equal to 0. So we need the partial of p with respect to x and the partial of p with respect to y, and we need both of those to be 0 at the same time for this to be the 0 vector. Okay, so I'll find the partial of p with respect to x first. Well, that's a constant times x as far as we're concerned whenever we're taking a partial derivative. The derivative of a constant times x is just the constant. Over here, I've got a constant times x squared. Well, we remember from Calculus 1, we bring our constant down, and then we differentiate x squared with respect to x. Well, that's just 2x. And this is another constant times x. The derivative of a constant times x is just the constant. So I've got 32y squared minus 2xy squared minus y cubed. And I just wrote it in that way because mathematicians like to do that. We always keep our variables alphabetical. It's not necessary. We know multiplication is commutative. Just feels nicer. It's a little bit more ordered. Many of us, including myself, including me, that's proper grammar, I think, find that satisfying. Okay, so we're taking the derivative of this guy with respect to y now. This is a constant times y squared, so we bring our constant down and we differentiate y squared with respect to y. That's 2y. And over here I've got a constant times y squared again. The derivative of a constant times y squared is the constant times the derivative of y squared with respect to y, that's 2y. And then for xy cubed, that x is treated as a constant. When we take a partial derivative to bring our constant down, and we take the derivative of y cubed with respect to y, that's 3y squared. So we get 64xy minus 2x squared y minus 3xy squared. And that's our partial with respect to y. Okay, now these are the components of my gradient vector. I need both of them to be 0 at the same time for the gradient to be 0. So we'll do that on the next page. I'm trying to get another piece of paper that I've already written on because I feel bad about all the paper that I go through. Have to at least reuse it, maybe recycle it, hopefully recycle it when school's open again. All right, so our gradient of p is this. Partial of p with respect to x is 32y squared minus 2xy squared minus y cubed. Partial of p with respect to y is 64xy minus 2x squared y minus 3xy squared. And we're setting that equal to the 0 vector. So that means this component and this component need to be 0 at the same time. So I need 32y squared minus 2xy squared minus y cubed to be 0 and 64xy minus 2x squared y minus 3xy squared to be 0. So we've got a system of polynomials, 2 polynomial equations and 2 unknowns, and we want them to be 0 at the same time. The easiest way to solve one of these is to factor each of these equations separately and then look at the factors. Look at all of the ways that we could possibly get this to be 0 and this to be 0. Normally I just start with one of them I force one of them to be 0, I think of all the different cases, and then I see what happens to the other one. So we have computed our gradient, we've set it equal to 0, and now we're solving the system of equations. For the critical points, x, y. Okay, so we factor this first one. Well, I look at this term, and this term. I notice that they all have a y squared in common. So I'll factor that out. Y squared times 32 gives me my first term. Y squared times a negative 2x gives me my second. And y squared times a negative y gives me my third. And I need that to be 0. And then let's look at partial of p with respect to y and see how that factors. Do these guys have anything in common? Well, they all have an x. They all have a y. So let's factor out an xy. They've got xy down here. And xy times 64 gives me my first term. Xy times a negative 2x gives me my second. And xy times a negative 3y gives me my third. Okay, so these are the factored forms of those partials up there. So I'm going to look at this in two cases. I will, I'm going to set the partial of p with respect to x equal to 0, and that will happen in two cases. Either this will be 0 or this will be 0. So we'll do that first. P sub x equals 0 when this product is 0, and the only way a product is 0 is if one of the factors is 0. So that means either y squared is 0 or 32 minus 2x minus y equals 0. Now, if y squared is 0, that means that y equals 0. So we're good there. And if that's true, well, I think I'll just rearrange that equation. We have y equals 2x minus 32. So if the partial of p with respect to x equals 0, either y equals 0, or we're on this line in the xy plane where y is 2x minus 32. Oh wait, did I do that right? Add y to the other side. It's actually 32 minus 2x. There we go. Yeah, okay. So y is equal to 0, or we're on this line. So those are our two cases. So case 1, let's say y is equal to 0. If y equals 0, then the partial of p with respect to x is 0. And if y equals 0, it looks like the partial of p with respect to y is also 0. Okay, you say that's not, what does that mean? Well, I guess that means that our function is optimized when y equals 0, and it does not matter what x is. Because if y is 0, or it's not necessarily optimized, if we've got a whole line of critical points is what I really should say. If y is 0, this partial is 0, and this partial is 0, regardless of what x is. X could be anything. If y is 0, I get 0 here and 0 here. So that means that if I'm looking for critical points, here are our ordered pairs, the set of all xy such that x equals anything and y equals 0. Those are critical points. You say, what? What is that? Oh, it's a bunch of critical points. All the points on the line y equals 0 count. They're critical points. Say, okay. Well, that was one possibility. The second case is that we're on this line. If we're on the line y equals negative 2x plus 32, then the partial of p with respect to x is going to be 0. And if that's true, then the partial of p with respect to y can be rewritten this way. So we've got x times y times the quantity 64 minus 2x minus 3y, and that has to be 0 as well. Well, that will be 0 if we're on this line when, well, excuse me, I need this to be 0, so I'm going to substitute negative 2x plus 32 for y, and then I'll find out what x has to be. So I've got x times y, and then I have 64 minus 2x minus 3 times y, whatever that is, equals 0. And we're on this line. So we replace y with negative 2x plus 32. And we see what we get. So I've got x here, negative 2x plus 32 here. And we've got a little bit of algebra to do inside these parentheses. No big deal, we can do algebra. So we distribute the negative 3. We get 6x and a minus 96. And 64 minus 96 is negative 32. So I've got negative 32. Negative 2x plus 6x is 4x. That equals 0. Okay. And I think we can factor further. Negative 2x and 32 have a factor of negative 2 in common, so let's factor that out. If I factor out negative 2 from this, I'm left with an x minus 16. These guys have a 4 in common, so I could factor that out. 4 times negative 8 would give me negative 32, and 4 times x would give me the 4x. And multiplication is commutative, so I can take that 4 and multiply it by this negative 2x. And that's fine. So, and I'll change the order over here, because addition is commutative with real numbers. Negative 8 plus x is the same as x minus 8. Okay. So, if this is our partial of p with respect to y, and it equals 0, and y is equal to this, so that the partial of p with respect to x is 0, then if that's true, then this also has to be 0. So, we've got a product, this times this equals 0. The only way that happens is if one of the factors is 0. So either negative 8x is 0, which means x equals 0, or x minus 16 is 0, which means x equals 16, or x minus 8 is 0, add 8 to both sides and you get x equals 8. Well, now that I have the x values, I can substitute those into this equation and find the corresponding y values. Well, when x is 0, according to this equation, if we're on this line and x is 0, y has to be 32. So y is negative 2 times 0 plus 32, which is clearly 32. So you've got a critical value. xy equals 0 and 32. If x equals 16, then y is negative 2 times 16 plus 32, which is 0. So we get xy equals 16, 0. And over here, we've got x equals 8. If we're on that line, we have negative 2 times 8 plus 32 for our y value. It's negative 16 plus 32, which is positive 16. So 8 and 16 are possible critical values as well, or are critical values as well. So we've got a line of critical values. All of these guys, x can be anything, y is 0. And then we've actually got two more. We've got this one, and that's actually a value on that line. So we really don't need to test it again. If we test this, we've automatically tested that. So we solved our system of equations for all the critical values. We've got 3 here, and then all of those on the line. Okay, and actually, we can rule out some of these. Let's think about it. What did the original question say? It said find 3 positive integers, x, y, and z, satisfying the following. That means y has to be positive. So x equals 0, y, or x equals anything, y equals 0, that's not a positive value for y, so we don't have to worry about that. our x and y all positive over here. Well, here y is 0 again. That's not part of our implied domain for this function, for this word problem. And x isn't allowed to be 0 either, so that guy's gone. So it looks like we only have one critical value to test. It's 816. And we were asked to maximize the function. Hopefully this is not a minimum. Hopefully this does not correspond to a saddle point. But we need to prove it now. I'm so glad we ruled out all those cases. That saved us a lot of work. So we solved the equations, the system of equations, for the critical points x, y. And then we did this. We ruled out any x, y let's say that do not satisfy the conditions of our problem. X and y had to be positive, so that guy's gone, and that guy's gone. So here x and y are positive. Hopefully the z that goes with that is positive as well, so it's satisfied. Like all the conditions are satisfied. But let's see. Okay, so we need to test this point. We're going to test this point now using the second partials test, and the second partials test requires us to take a bunch of second derivatives. So keep in mind, those are our partials with respect to x and y. And I'm going to get another piece of paper so that we can solve this now. Okay. I'll just put that like that so we can still see it. Okay. So we're using the second partials test. To determine if that point that we found, what was that point again? 816. So determine if our critical point 816 corresponds to a min, so a relative min, a relative max, a saddle point, or if it's impossible to tell. So that's the plan. Now whenever we use the second partials test, the first thing we'll do is we'll find the Hessian. And I've got my first partials right here. And this Hessian, remember, for a function of two variables, I guess it's a P, not an F, is the matrix of second partials. In the first row, you start with the partials with respect to x. In the second row, you start with the partials with respect to y. And then you take the derivative again with respect to x and then y, and with respect to x and then y. You put those in a matrix, that's the Hessian. Okay, so we need these four partials. So to find the second partial with respect to x, we take the partial with respect to x of the first partial with respect to x. So I'll just write that in right here. 32y squared minus 2xy squared minus y cubed. That has no x's in it, so it's constant with respect to x, so we get 0. Here I've got a constant times x. The derivative of a constant times x is just the constant, and a negative 2y is constant when we're taking a partial derivative with respect to x. And while taking a partial with respect to x, y is constant, so y cubed is also constant, so the derivative of that guy is 0. So our Hessian has a negative 2y squared in that first row, first column entry. Now we'll take the partial with respect to x and take its derivative with respect to y. Oops. Yes, that's what I want to do. So I'm taking the same function from the last one, the last partial derivative, and now I'm differentiating with respect to y this time. Well, the derivative of 32y squared with respect to y is 32 times 2, which is 64, times y to the first. And then here I've got a constant times a function of y, so I bring my constant down, and I take the derivative of y squared with respect to y. So that's just a 2y. And then I take the derivative of negative y cubed with respect to y, and that's 3y squared. So we end up with 64y minus 4xy minus 32y squared. And I didn't leave myself nearly enough space right there to write that partial. So I'll say 64y minus 4xy minus 3y squared goes there. And this is going to be the same. If I've done everything correctly, the partial with respect to y and then x, that mixed partial, should give me the same answer. Now, I'm not sure that I've done everything correctly. Sometimes I make mistakes. That's okay. So we'll take the derivative with respect to x of the partial with respect to y. So we're going to substitute that in right here. We should get the same answer as we got on the last one. It's always a good idea to do it both ways unless your function is really tedious and you say, I don't want to do that again. Just say that they're the same. If you're dealing with a polynomial function, you know that's going to work out just fine. But sometimes we want to check our work just in case we made a little error. Now I'm taking the derivative with respect to x this time. I've got a constant times x. The derivative of a constant times x is just the constant. The constant is 64y. Here I've got a constant times x squared, so I bring my constant down, and then I take the derivative of x squared with respect to x, so that gives me 2x. And now I've got a constant times x here, so I bring the constant down. Derivative of a constant times x is just the constant. Do I get the same answer as I got last time after simplifying? Yep, I sure do. They're the same. That's good. That means I did it right. Probably, unless I did it wrong twice in exactly the same way. No, it's probably right. And now we take the second partial of p with respect to y. So I've got this guy, and I'm just taking the derivative with respect to y. Partial derivative with respect to y. Okay, so this is a constant times y. The derivative of a constant times y is the constant. And I've got another constant times y. The derivative of this constant times y is that constant. And that's a constant times a y squared. Bring the constant down, and then multiply by the derivative of y squared with respect to y. And so we get 64x minus 2x squared minus 6xy. 64x minus 2x squared minus 6xy. Okay, so that's our Hessian. Is that weird line in the middle? Sorry, because I anticipated it being smaller. That's okay. But now we need to evaluate it at our one critical point that was in the implied domain from our problem and see if the determinant is positive, if everything is what it needs to be so that we can maximize the function p. Because remember, that's what we were asked to do. We were asked to try to find the maximum value of p. Okay. So let's evaluate our Hessian matrix at 816. And our hope is the determinant of this is positive, and the second partials with respect to x and y are just right so that we maximize this function p. We shall see. Actually, I'm just going to write this for right now. And let's just compute those partials, second partials at the point down here and separately. Okay, second partial of p with respect to x was negative 2y squared. So I have negative 2 times 16 squared this time. And I'll use a calculator for my arithmetic. So I have negative 512. Alrighty. And let's take the mixed partial, derivative with respect to x and then y, evaluated at 816. So I've got 64 times my y value, which was 16, minus 4 times my x times my y, x is 8, y is 16, minus 3 times y squared, and y is 16. So I'll use calculator for arithmetic again. 64 times 16 minus 4 times 8 is 32 times 16 minus 3 times 16 squared. So I get negative 256. Okay, and the mixed partials were equal. So the partial with respect to y and then x at that point is the same as the partial with respect to x and then y at that point. So I get that. Okay, so we still have negative 256 there. Now I want to take the second partial of p with respect to y that we already calculated and substitute in x equals 8, y equals 16. So we've got 64 times our x value minus 2 times our x squared minus 6 times x times y. X was 8, y was 16. So I have 64 times 8 minus 2 times 8 squared, 64, minus 48 times 16. We get negative 384, provided I typed that in my calculator correctly. All right, so let's take the determinant of that matrix. And that was for a different problem. So we get negative 512 times negative 384 minus 256 squared and I get a very large positive number, 131,072, definitely positive. And next thing we do is we look at the second partial of p with respect to x at that point. It was negative 512. It's negative, so that means the graph is concave down in the x direction. And supposedly, if d is positive, then the concavity in the x direction and y direction are the same. And it's true. This is concave down, and this is concave down. It's concave down in both directions. It always works out that the fact that they told us would be true is true. That's pretty cool. So we know we're at a relative max. That's good. So p is maximized. At x equals 8, y equals 16. Now we have to make sure that the z value that goes with x equals 8, y equals 16 is positive as well to make sure that we're actually answering the question. And remember what they asked us. Make sure you always go back and check that question. Some students, they sort of roll their eyes at me when I say, hey, go back and read the question again and make sure you're answering it. And they're like, of course I'm supposed to do that. I'm reminding you because a lot of people don't. A lot of people would just do what we just did and celebrate and leave. Don't be that person. We didn't answer the question yet. The question asked us to find 3 positive integers, x, y, and z, that satisfy the following. Their sum is 32, and p is maximized. This product is at a maximum. And we've just discovered that when x is 16, or excuse me, when x is 8 and y is 16, p is at a maximum, so that's good. But we still haven't answered the question yet. We need to state the integers, x, y, and z, such that all of this is true, and make sure that the z value that goes with the x and y we found is also positive, so everything is satisfied. So let's find the z that goes with the x and y. We know x plus y plus z has to be 32, so we can use that to find z. So substitute x equals 8 and y equals 16. So you get 24 plus z equals 32. So z is 32 minus 24. So that's 8. Okay, so x, y, and z are all positive. They're integers, and p is maximized there. So the question said, find the 3 integers that satisfy that. The answer is, the 3 integers are 8, 16, and 8. And that's it. We've answered the question. I wanted to do one more example, something that is a little bit less like a problem from a math book and sounds a little bit more like a real-world application problem. It is somewhat contrived, but at least it sounds like a real-world problem. I'm going to do that in the next video because we're running out of time. But remember what we just did. When we're optimizing functions of several variables, we use the second partials test. But in an applied optimization problem in this class, you're going to need 2 things. You're going to read the problem statement and you're going to look for the objective function. That's the function that you're optimizing. If that is a function of more than 2 variables, you're going to have some constraints. There's going to be some equation out there that relates the variables to each other so that you can write this objective function entirely in terms of 2 variables, not 3, not 4, not however many it started with. So you want to write this in terms of 2 variables so we can use the second partials test as it's stated in Calculus 3. Then you optimize the function using the second partials test. But you want to keep the constraints in mind, not just the singular constraint equation, but everything else that they told you, just like we did in this problem. We needed 3 positive integers that satisfied this. The fact that we were looking for positive numbers and integers, that would have come into play as we were solving this problem. It did come into play, the fact that they were positive. We found some critical points that had zeros for x and zeros for y, that we weren't interested in those. So we could throw those out immediately. If I got a fraction, I didn't, but if I had gotten a fraction from this, I would say, oh, it's not an integer, throw it out. So we optimize the function the way we did previously, just using the second partials test, but we throw out any critical points that don't satisfy the constraints or the requirements of the problem that we were given. After we do that, then of course we use the second partials test to make sure we found the min or the max that we were trying to find. I always go back and reread the problem statement and make sure I've answered the question being asked, so that if somebody asks me for a maximum height, I'm not giving them the time when we're at a maximum height. I'm not giving them an ordered pair when they're asking for something very specific. So we always go back and find out what they were asking and then make sure we answer that question. So we'll do another example in the next video.